Let us start lecture 28, and the course is phase diagrams in single component and binary systems. And today we will discuss the same topic what we have started in our last lecture. We will be treating now condensed solution, which will be either solid or liquid, and then we try to measure Gibbs free energy of mixing when we try to mix a number of components. In fact, then gradually we will move to binary systems. In fact, in the last lecture we started calculating the partial quantity, which is nothing but partial molar Gibbs energy of a component in a solution that can be found out from the knowledge of Gibbs molar free energy of the solution and the slope of that particular plot between Gibbs molar free energy for the solution with the composition, and that two relations. In fact, we have tried with binary system where we have tried to mix A and B, and then we actually found out those two formulas. So, today's lecture would be on condensed solution, and we will try to measure Gibbs free energy of mixing. And the last lecture what we have found? So, we have found Gm equal to Xa Ga bar plus Xb Gb bar. This formula we started where Gm is the molar Gibbs free energy of solution, or we can say homogeneous mixture, and this formula is applicable for ideal mixture or even a real mixture. Whether in case of ideal mixture, definitely those constituent molecules will not have any interaction between each other, but in case of real mixture we can have interactions, fine, but both the cases it will be applicable. So, that means this formula will also be applicable for the condensed solution. So, this will be applicable, this particular formula can be applicable for condensed homogeneous solution, or in fact in the gas mixture, you can say ideal gas mixture. Ideal gas mixture, both the cases it can be applicable, where Gm is molar Gibbs free energy of the solution and Ga bar is partial Gibbs free energy of component A in solution, and Gb bar is basically same thing. This will be free energy of component B in the solution, fine, and this is basically for A and B solution, and we have started with Na number of Na moles of A and Nb moles of, this is number of moles of A as well as B before mixing, and after mixing actually we are getting the total mole will be Na plus Nb, and from there actually we are getting Xa and Xb, which are mole fractions. And then we found out that Ga bar equal to Gm plus Xb dGm dXA, and Gb bar equal to Gm plus Xa dGm dXb. And in fact, these two formula will be used heavily while calculating phase diagrams, and so these two formula will also be used for calculation of a quantity, free energy quantity, when we try to measure the difference of free energy quantity when the particular component is in pure condition as well as that particular component in the solution condition. So, in fact, this will be also used up for calculation of delta G A m this quantity as well as delta G B m for this quantity. So, these are basically nothing but partial molar of ith component after mixing in solution. Fine. So, this is different than this quantity, this is not same as this. So, we will see that. So, this is basically you can say when we mix multiple components to form a solution. So, that time each individual component, if we try to find out what would be the difference of free energy between the free energy after mixing minus the free energy before mixing of that particular component. So, that is basically this one. Okay. So, that is what, and but these two are basically chemical potential of individual component in the solution, okay, or partial molar quantity of individual component in the solution. So, this is the difference and this is the quantity in the solution. Okay. So, now we try to measure, we have to measure these two quantity, this one and this one. So, that if we measure those two, then we will definitely be able to measure delta G mix of solution, whether it is for solid and liquid. That should be our purpose. And this mix, sometimes it is also written as molar mixing quantity, and remember this is for 1 mole solution. Fine. We have to finally measure this, that is basically the gives free energy of mixing in case of condensed solution. So, in order to treat that, we need to know few things. Okay. So, in fact, when we talk about any condensed phase, that phase will be in equilibrium with the gaseous phase or the vapor phase of that particular component, and that gaseous pressure exerted by that gaseous phase in equilibrium with that particular component in a closed system will be function of that temperature where that system is kept, and that particular pressure we call it saturated vapor pressure of that component. Whether you take pure substance or you take substance in a solution, both the cases that particular very component would have its own saturated vapor pressure. Okay. So, now in order to find out the equilibrium condition, and that time we just simply go from condensed phase to the vapor phase, and if we can see the equilibrium condition in the vapor phase, that can be extended to the condensed phase. So, that is the philosophy. So, we will be dealing with gas phase, that will be easy to deal with, and that gas phase dealing we have already done in case of ideal phase, ideal gas mixing. Okay. So, that concept will be drawn to this particular case when we try to treat condensed solution, which is either solid or liquid. So, in order to know that, we need to understand couple of things. So, one is how those components in a solution, of course condensed solution, are interacting with each other, okay, or the molecules or atoms of those components in a solution are interacting each other. Now, we know that any gas system, okay, whether it is a real gas, even if we take real gas, if we go to very high temperature as a reasonably very low pressure, that time those molecules of those real gases would also lose their interaction possibilities. In fact, those interactions can be ignored or neglected. Okay. So, that time even a real gas at a very high temperature and low pressure will turn into an ideal gas. Okay. That is what we have learnt. Okay. So, we have learned that high temperature and low pressure, in this condition even real gas can become ideal gas. So, real gas means where we have interaction between atoms or molecules of those gas system, and here ideal gas is basically no interaction. Fine. So, no interaction between atoms and molecules. Okay. So, we know about that, but in case of condensed phase or condensed solution or condensed pure metal, or if we take solution definitely. So, let us say when we take condensed solution, okay, so that time we have interactions between atoms of the components. And here if we see, we have treated all the mixture of ideal gases, and this becomes easy to deal with. And that actually we have found that if we try to find out delta G mix, we have seen that this formula, if you recall. Okay. So, this formula we have found, and we have tried to calculate del G mix when we mix multiple ideal gases. The treatment was relatively easy, but when we talk about condensed solution, interaction between atoms of the components, they do exist. Okay. And that interaction will be decided by many factors. Okay. So, that interaction, this interaction will be decided by many factors like atomic size, electronic configuration or electronegativity, or we can have electron to atom ratio. All those factors will be there, and those interaction, in fact, that would also influence the bond energy. So, in fact, those interaction between atoms would lead to a bond between those atoms, and that every bond would have some specific energy, and those bond energies will be affected. And finally, this would also affect the degree of solubility or even reaction. Okay. So, those atoms can react each other and then form a different phase altogether. Okay. So, that means you see it is not very easy to deal with the condensed solution when we try to understand the equilibrium conditions. Okay. So, and that is what the solution behavior. So, the entire thing, the solution behavior, and it is basically a thermodynamic solution, thermodynamic behavior would also be decided, would also be dependent on these many factors. So, in order to treat that solution behavior in case of condensed solution, we need to bring in two concepts. One concept lead to one particular law called Raoult's law. So, another one led to Henry's law. In fact, these two laws will actually bring in a relation of G with saturated vapor pressure of any component in the condensed solution. Fine. So, let us look at Raoult's law first. Now, if we let us say we have a system, it is kept at a particular temperature, let us say this is the closed system and we have pure liquid, let us say we have pure liquid A and this is at a particular temperature T, and initially this system was evacuated and then we keep liquid pure A is kept. Okay. So, once we keep that, we have understood before when we try to understand the equilibrium in case of single component system, once we do that, vapor will start forming. And that vapor formation will stop when we reach equilibrium vapor pressure, which is basically saturated vapor pressure, which is P naught A, let us consider P naught A, which is a saturated one, and that is basically specific to the temperature where we have kept that particular system. So, now here we will form vapor, and both for in case of A we have a liquid vapor A as well as the vapor of A in equilibrium with the pure liquid A. So, now if we see this particular surface, which is the liquid vapor interface, A atom will start leaving liquid surface and be part of the vapor phase. Okay. So, now that means there should be a rate, that means a number of A atoms leaving the surface and joining the vapor phase at particular per unit time, that would be dictated by REA. REA is what? Because we are talking about liquid vapor transformation. So, this is a rate of evaporation of A, that means the number of atoms of A joining the vapor phase from liquid surface. Fine. So, similarly, once we have that particular process, the rate of evaporation, there would be also the parallel process that will start happening, which is called RCA, which is nothing but the rate of condensation. Rate of condensation of A is basically again the number of A atoms joining liquid surface from vapor phase. Fine. At equilibrium, which is specific to that temperature, REA should be equal to RCA. Okay. And this C is nothing but the condensation, E is basically evaporation. and we have only one component which is A. Now, if I try to look at this RE, in fact, RE, the rate that RE will be a function of course, the activation barrier as well as, or I would simply say E star, which is the activation barrier for the atoms to leave liquid surface and join vapor phase, and another one the temperature. Okay. Okay. So, that will be the deciding factor. In fact, this activation energy, so E star is basically activation energy. Activation energy, and this activation energy evolves because when we look at that atom position on the liquid surface, these are let us say A atom position, this is the surface, fine. So, these atoms are actually sitting in a energy well. So, this in order to leave this atom from the surface and to join the liquid to vapor, it has to cross this activation barrier. Okay. So, this is nothing but E star, fine, and this activation barrier, this particular activation barrier and this RE relation could be done in this fashion. So, there is a rate of N atom leaving the liquid surface is equal to, is basically proportional to number of A atom which have acquired activation energy more than E star divided by the total number of N atom that is there on the surface. So, this is proportional to that. In fact, that is also proportional to exponential minus E star by kT. Here we have used K because we are talking about atom leaving the liquid surface and joining vapor phase, fine. So, now when we take that, that means it suggests that the rate of evolution, and where N star is basically number of A atom on the surface of liquid acquiring energy greater than E star, and N is the number of total A atom. On the liquid surface, fine. So, now once we have that, so that means we see that if we reduce this and if we increase T, we will see that RE will also go up. Okay. So, that means evaporation rate would also go up. In fact, that would lead to higher PA naught. The partial pressure, the saturated vapor pressure would also increase. And now, if we consider where from this particular activation barrier is evolving, because once we have A atom, it is a pure condition. So, that means there will be a single type of bond, AA bond, okay. And this AA bond, in order to break that AA bond, you have to supply energy, and then only A atom will move, will break away from the surface of liquid and join vapor phase. So, this bond would lead to bond energy, and in order to break that, you need activation energy. So, that is what those atoms are basically in an energy well. These are basically all energy well. Now, come to other situation. Once we know that RE A equal to RCA, and now if I try to find out RCA, which will be which will be proportional to P A naught. Why? Because if I try to find out what is RC, that is the rate of condensation. So, that means rate of condensation means the number of atoms in the vapor phase should leave the vapor phase and join the liquid surface. So, that means the vapor pressure, the saturated vapor pressure is actually a parameter which will decide that how many atoms of A would join the liquid surface from the vapor to liquid. Okay. So, this is proportional to, not equal, proportional to P A. So, now we can write that R E A is also proportional to P A naught, and then we can write R E A equal to K P A naught, and where K is the proportionality constant. Fine. Now, this is with respect to pure A, and if we consider that there is a pure B also, and let us say this is also liquid condensed phase, that case also the similar treatment we can have, and we can find out R E B would be equal to K prime P B naught, and where we have put K prime is basically another proportionality constant. Okay. Now, let us look at what happens if we talk about AB solution. If we talk about AB solution, then so we have now 3 bonds AA, BB and AB. These are the 3 bonds, and every one would have some bond energy EAA, EBB as well as EAB. Okay. So, these 3 bond energies would exist. Now, this bond energy would actually decide what will be the depth of energy well. So, they will decide depth of, okay, or it can actually decide E star, the activation energy that will be needed for evaporation. Now, if we think that if we let us say we take AA equal to EBB equal to EAB, all the bond energies are same. We also take that atomic size of A and B atoms are atomic size are same. Okay. And another thing is we take the composition of, and how we decide the composition in case of binary solution. Let us say this is a liquid solution. Okay. It will be decided by XA and this will be decided by XB of the surface and bulk are same. So, that means the number of A atoms on the surface or B atoms on the surface would be same as the bulk of the system, and we know that the surface, from surface only A atom or B atom can join in the vapor phase. Okay. And in the solution also, that individual components A or B would also have their own partial pressures, which will be equilibrium partial pressure, which will be decided by the temperature of the system. Fine. So, it will have its partial pressure, this will also have its partial pressure. Fine. Now, since this is considered, so that means this also, and in fact all those, this would be indicating that the number of A atom would be same as would be same as bulk. Similarly, it will be applicable for B, but these two are interesting. These two would allow the energy well depth that would actually allow the depth not to change because of addition of A or B, irrespective of whether we are adding A into B or B into A. Because whatever you do, since they are active, those bonds are equal, whether A would have less number of B neighbor or B would have less number of A neighbor, still since the bond energies will be same, so the energy well height would remain same. Okay. So, that means that this would also lead to a condition that REA or REB in the solution would be intrinsic. That means, it does not depend on the composition. Fine. So, now once we have that situation, since it is intrinsic, now if we try to find out what will be the relation of PA and PB with their respective pure condition saturated vapor pressure, that we can also find out. Now, if we try to see for in case of A in B, if we try to see that, since we know that the number of A atoms on the surface would be same as the bulk, and A atom whether it would have more B neighbor or more A neighbor, the energy well height remains same. So, that would actually reduce saturated vapor pressure. Fine. So, of A as well as B, saturated vapor pressure of A and B would reduce in the solution as compared to the vapor phase partial pressure, vapor phase pressure when these two components are in pure condition. Okay. So, that reduction, and this is also intrinsic, this rate of evaporation or REB are intrinsic. Okay. So, that time and only the A atom from the surface would actually go to vapor phase, or B atom on the surface would actually go to vapor phase, and the compositions are same in the on the surface as well as the bulk. So, then definitely there would be a reduction of evaporation rate of A by XA quantity. So, this is let us say REA in solution, this is in solution, fine. So, there will be reduction by XA, which should be equal to K into PA, because the PA is the saturated vapor pressure. So, these two are of A as well as B when solution is considered. So, that means this would be this, as well as RE prime B would be equal to REB in pure into XB. So, that will be the reduction, which would be equal to K prime PB, because in case of B we have considered the constant as K prime, in case of A we have considered the constant as K. So, now we also know that RE is nothing but K PA naught into XA equal to K PA. So, this leads to one equation PA equal to XA PA naught, and this one also would lead to K prime P B naught x b equal to P B K prime. So, this K prime here also this K would get cancelled. So, finally, we get P B equal to x b P B naught. So, these two equation are basically nothing but Raoult's law, and we have taken a binary system. And when we try to see that when an A component follows Raoult's law, so we say that A is following Raoultian behavior in the solution. Similarly, it can be applicable to B also. That time we will say that B solute would behave as would show or would exhibit Raoultian behavior. Okay. So, now we see that partial pressure of A as well as partial pressure of B in the solution, that would be specific to that temperature, definitely the temperature what you have considered, but that can have a simple relation with the partial pressure, not partial pressure. Here now we are considering pure case P A naught and P B naught, and P A and P B basically the partial pressure, but that is also the saturated vapor pressure of A and B in the mixed vapor phase when we consider the solution. Okay. So, this simple relation can be used in order to find out del G mix in case of condensed solution also. So, now interestingly you see that we are actually trying to take the vapor phase equilibrium or to deal with the condensed solution. Okay. So, these will be taken up in the subsequent lectures in order to find del G mix. But at least from these analysis we know that we can treat a condensed solution with the help of the vapor phase that is in equilibrium with that condensed solution, and then finally, we get fantastic equation which will end up giving us del G mix for the condensed solution. So, let me stop here, we will continue our discussion and in the next lecture. So, there we will consider a real situation which is basically which will lead to Henry's law. Okay. So, till then, thank you very much.